So in this video, we're going to talk about projectile motion. A couple videos ago, we talked about free falls. And remember that in free falls, say I throw a ball up in the air, it's going to go straight up and then straight back down. So the initial velocity it has is in the upwards direction. And then the only other force acting on this ball is gravity, which is in the downwards direction. So it's easy to figure out, time it takes to go up, its maximum height, time it takes to go down, all of these factors, because the vectors that I have in this scenario are in either just the up or downwards direction. Now, in projectiles, it's slightly different, because in projectiles, I have an object moving in a shape that usually looks like this. Okay, so I throw the ball up at some angle. So this would be like my initial velocity, and here's my angle. So I see I have both, vertical movement up and down, and then I also have horizontal movement. But just like in free falls, the only force acting on the projectile is gravity in this case. If we neglect air resistance, which we will, just like we did in free falls. Okay. So on the next page, let's consider what would happen to a projectile if there is no gravity. So we know typically a projectile will look something like this. Okay, let's just draw the ground here. So let's say this is the ground. Alright. And I throw it up at some angle with some initial velocity. So if there was no gravity, the projectile would simply continue up in that direction. Just like that, right? So when we talk about Newton's first law, everything in motion stays in motion. That basically means that if it has a velocity, it will continue on at a constant velocity unless some other force is acting on it. But we know that in the real world, the force that's acting on this is gravity. And it's important to note that gravity is the only force acting on the projectile if we neglect air resistance. Okay, so it's sort of difficult to look at this gravity vector, this guy, and the initial velocity vector and add them together, because if we notice, they aren't in a line, right? They aren't like collinear, and they don't really intersect each other at right angles like we saw in the last video. So what I can do is break up this initial velocity vector into two components, the horizontal component and the vertical component, and look at the two components individually. Okay, so let's say that in this scenario I throw a ball at an angle of 30 degrees above the horizontal, so this is 30 degrees, with an initial velocity of, let's say, 20 meters per second. Okay, so how could I rewrite this in terms of the horizontal component, which is this guy, and my vertical component, which is this guy? Okay, so we see that this makes a right triangle. Alright, let's call the vertical component y and the horizontal component x. And remember from the last video that I can use trig to solve for x and y. So I would say, okay, sine of 30 equals y over 20. Solving for y, I get y equals 20 sine of 30. Alright, and then for x, I can do a similar setup. X equals, actually I'll set up the trig function first. So we would do cosine of 30 equals adjacent, which is x, over hypotenuse, which is 20. So solving for x, we get x equals 20 cosine of 30. Okay, so x equals 20 cosine of 30 is the velocity of this ball with respect to the horizontal. So this is in meters per second. And then y equals 20 sine of 30 is the velocity of the ball with respect to the vertical component. So this is in meters per second as well. And you should remember from the last video that in general, I can rewrite any horizontal and vertical component in terms of x and y. And those formulas are x equals initial velocity times cosine of the angle, and y equals initial velocity times sine of the angle. Okay, so those are the formulas that we will use a lot when we solve projectiles, and we just used it or them in this scenario. Okay, so let's see how we can apply that to actually solving a projectile problem. Okay, so we know that the horizontal component is equal to 20 cosine 30 meters per second. And that's really about, cosine of 30 is root 3 over 2. We can simplify that down to about 17 meters per second. And then I also know that my vertical component is 20 sine 30, and sine 30 is 1/2. So this is really just the same as 10 meters per second. Okay, and I know that that makes this resulting vector here, okay, which we already have determined has an angle of 30 and initial velocity of 20 meters per second. Okay, but we're not really concerned with the vector in red, really just the two vectors in black. And then we also know that gravity is pushing down well, for easy numbers, we'll say 10 meters per second squared. Okay, so if we look closely, we see that gravity will affect the vertical component, this guy, the 10 meters per second, in the vertical direction, but not the horizontal component. Think of it as like if you roll a ball across the table, right? The ball is moving horizontally. Gravity isn't really affecting it because it's the horizontal movement, because it's going horizontally, not in the direction of gravity. Okay, so really the only reason why the ball hits the ground is because of gravity, and the time at which it hits the ground is dependent on the vertical component of the velocity function, not the horizontal component. Okay, so if we want to figure out how long is the ball in the air, we need to take into consideration the vertical component and gravity, not the horizontal component. Okay, so let's make a chart on what we know with respect to the vertical. So, velocity, final velocity, time, change in position, and acceleration. And we'll also make one with respect to the horizontal. Okay, so we know that the initial velocity with respect to the vertical is this right here, so 10 meters per second. We don't know the final velocity. We don't know the time. Now, do we know displacement? So I'm considering, we're looking to find how long is the ball in the air, let's say. So let me draw like a picture of a projectile. So it might look something like this. Okay, so in terms of vertical displacement, we don't have any. I start here and I end here, so my vertical displacement is actually 0. I'm not any higher or lower than where I originally was. Okay, so if I'm looking for total time in the air, my vertical displacement is 0. Notice that my horizontal displacement for total flight time is not 0. I definitely move significantly over to the right looking at this diagram. Okay, and then acceleration in the case of vertical movement is gravity, which is in the opposite direction as the vertical component, so we will say it's negative 10 meters per second squared. Okay, now let's look at the horizontal component. So we know that the initial velocity with respect to the horizontal is this, 17 meters per second. I'm going to skip final velocity and come back to it. We don't know the time. We don't know displacement. Remember that displacement in terms of the horizontal is this distance, which we don't know. Okay. And then acceleration. The acceleration with respect to the horizontal is actually 0. And that's because gravity only works in the up and down direction, not side to side. And there's no other forces acting on this ball if we neglect air resistance. So acceleration with respect to the horizontal is 0. Which also brings us back to final velocity. If acceleration is 0, that means I have constant velocity. So my final velocity with respect to the horizontal is 17 meters per second. Okay, as well. So now let's see if we can figure out total flight time. Okay, so if I were to look at the horizontal component, because velocity is 0, if I were to consider that alone, it would be like the ball never hit the ground. But because of gravity and because I have a vertical component as well, the ball does hit the ground. So to determine flight time, I need to use the vertical component. Okay. So we also know from previous lessons that final velocity equals initial velocity plus acceleration times time. And we also know that delta x equals initial velocity times time plus 1/2 acceleration times time. Okay, so using this first equation, this one doesn't help me because I don't know final velocity and I don't know time, so I have two unknowns. So let's use the second equation because I know displacement, I know initial velocity, and I know acceleration, so we can find time. Okay, so I'll plug in on the next page. So delta x equals initial velocity times time plus 1/2 acceleration times time squared. We saw that displacement was 0 and that initial velocity was 10, so I can plug those two in. Oh, and then acceleration is negative 10. So 0 equals 10t plus 1/2 negative 10t squared. And just as a side note, the difference with the plus and the minus, so I define the upwards direction as being the positive direction, so initial velocity would be positive 10 meters per second, and since gravity is in the downwards direction, and I'm saying that downwards is a negative direction, acceleration would have to be negative. Okay. So I can solve for t. 0 equals 10t minus 5t squared. Divide by 5, so 2t minus t squared equals 0. Factor out a t, so t times 2 minus t. And solving for t, I get that t equals 0 and t equals 2. Okay, and that's in seconds for both of them. Okay, so we know that the ball will have a displacement, a vertical displacement of 0 at time 0 seconds and 2 seconds. And looking at this small graph over here, that makes sense, because they're basically saying that here is 0 and here is 2. So it has a vertical displacement of 0 when it's at its initial point at time 0, and when it's at its final point at time 2. Okay, so total flight time is 2 seconds. Alright, so really this is total flight time. Now let's say I want to find the range, which is horizontal displacement. So how far did the ball go in that 2 seconds? So I look at my table. I now know that time is 2 seconds. This is 2 seconds. So now I can find displacement with respect to the horizontal, just again by plugging in to the second formula, this one right here. Okay, I'll do that on the next page. So we're solving for displacement of the range with respect to the horizontal, so that's what we're looking for. We know that the initial velocity with respect to the horizontal is 17 meters per second. This right here. We know that the time is 2 seconds and the acceleration is 0. 17 times 2 plus 1/2 times 0, 2 squared. Okay, so this term basically just goes away. Okay, so delta x equals 2 times 17, which is 34 meters. Okay, so the range of this is 34 meters. So this distance is 34. Okay, so from here to here is 34. Now let's say we want to find maximum height. So we're looking for what is the height of the ball at its maximum point. So what is the distance right there? Okay, so an important note about projectiles is that they are symmetrical. Okay, so the ball will obtain its maximum height halfway through its motion. So we know that its total flight time is 2 seconds. So the ball will obtain its maximum height at 1 second. Okay, so what I can do is now plug into the vertical component to find its maximum height, which will be its displacement with respect to the vertical. Okay, so now delta x again equals vi times t plus 1/2 at squared. And so we're trying to find the displacement with respect to the vertical at time 1 second. I know that the initial velocity of the vertical was 10 meters per second. The acceleration is still negative 10 meters per second. So I can plug in. Okay, and I get 10 minus 5 equals 5 meters. So the maximum height is 5 meters. And just to reiterate, that's going to occur halfway through this projectile's motion. So if its total flight time is 2 seconds, its maximum height will be at 1 second. Okay. Now, a note about when it's at its maximum height. So when it's at this point right here, remember when we did free falls that when the ball is changing direction, so, when I throw it up in the air and it goes from moving upwards to moving downwards, the velocity with respect to the vertical is 0 meters per second at that point, because it's changing direction. So with respect to the vertical velocity, it's 0. The horizontal velocity stays constant the whole time and will remain at 17 meters per second. So one last question you might be asked is, what is the speed of the ball when it hits the ground? Okay, so we know that the speed with respect to the horizontal is 17 meters per second, but we don't know what it is with respect to the vertical. But I can find it because we know this formula. We know that VF equals VI plus acceleration times time. With respect to the vertical, we know that initial velocity is 10 and acceleration is negative 10 meters per second. We know time is now 2 seconds. So I can say 10 minus 10 times 2. 10 minus 20 equals negative 10 meters per second. So this is kind of interesting. We see that initial velocity and final velocity with respect to the vertical, in terms of speed, are the same, but they have the opposite direction. So that should make sense because it will actually hit the ground at the same speed that it was projected. Okay. So we've kind of covered pretty much everything that you need to know with in regards to projectiles. In the next video, we'll cover a formula on how you can find the range of a projectile by just knowing like initial velocity and the angle instead of having to solve for time first. This is sort of like an extra bit of information, but this is really, what's in this video here is really everything that you would have to solve for involving projectiles.